Artificial intelligence feels weightless. You type a question. A machine answers in seconds. No smoke, no noise, no factory. It feels like pure information. But behind every answer, there is a physical world. Buildings full of servers, power lines under pressure, water used for cooling, land being developed, communities asking who pays the price. So the real question is not only what AI can do, it is this: how much does artificial intelligence actually cost the world? For most people, AI begins on a screen. A chatbot writes an email. An image generator creates a picture. A search engine gives a faster answer. A phone suggests what to type next. It feels clean. It feels instant. It feels almost invisible. But AI is not invisible. Every prompt has to be processed somewhere. That somewhere is usually a data center. A data center is a building designed to house thousands, sometimes hundreds of thousands, of computer servers. These servers store information, move data around the internet, and now, increasingly, run the systems behind artificial intelligence. From the outside, many data centers look boring. They may look like warehouses, plain walls, few windows, heavy security, a fence, a parking lot, a building most people would drive past without noticing. But inside, they are some of the most important buildings in the modern world. Rows of machines run day and night. Fans push hot air away from processors. Cooling systems work constantly. Backup generators wait in case the grid fails. Fiber optic cables carry information at incredible speed. This is where the digital world becomes physical. Every photo stored in the cloud. Every movie streamed at night. Every online payment. Every map search. Every AI answer. All of it depends on machines that need space, power, cooling, maintenance, and protection. And as AI grows, these buildings are growing with it. The International Energy Agency says global electricity consumption from data centers could more than double by 2030. It could reach around 945 terawatt-hours. That would be slightly more than Japan's total electricity consumption today. That number is difficult to imagine. So think of it this way. A single AI answer may feel tiny, almost nothing. But millions of people asking questions every hour becomes something very different. It becomes a system, a habit, a new layer of daily life. And every new layer of digital life needs infrastructure beneath it. That does not mean AI alone uses all of that power. Data centers also support cloud storage, streaming, banking, online shopping, business software, video calls, social media, and the everyday internet. But AI is becoming one of the biggest drivers of new demand. There is a reason for this. Older internet services often move or store information. AI systems do something more intense. They calculate, they compare patterns, they generate new text, images, code, video, and predictions. They do not simply find information, they produce an answer. That answer is created through computation. And computation needs electricity. There are two major phases that matter. The first is training. Training a large AI model can require enormous computing power. The system studies huge amounts of data and adjusts billions of internal settings. This process can take powerful chips, long-running times, and large amounts of energy. The second phase is daily use. This is called inference. Every time a user asks a question, creates an image, summarizes a document, or asks for code, the model has to run again. One request is small, but when millions of people use AI every day, the total becomes enormous. This is why tech companies are racing to build new data centers. In some places, these buildings are becoming as important as factories were in the industrial age. But the new factory does not produce cars or steel. It produces computation. And computation is becoming one of the most valuable resources on Earth. This creates a difficult question. Where will all that power come from? Some companies are buying renewable energy. Some are investing in nuclear power. Some are improving chip efficiency. Some are designing better cooling systems. These changes matter, but demand is growing so quickly that efficiency alone may not solve the problem. The United States Department of Energy reported that data center load growth has tripled over the past decade. It could double or triple again by 2028. That kind of growth puts pressure on electric grids. In some regions, new data centers can compete with homes, factories, and local businesses for available power capacity. This does not always mean the lights go out, but it can mean expensive grid upgrades. It can mean delays for other projects. It can mean difficult decisions about who gets connected first. Because data centers are not built in the abstract, they are built near real towns, real roads, real water systems, real power lines, real people. For local officials, a data center can look attractive. It can bring investment. It can bring tax revenue. It can make a region look important in the digital economy. But residents often ask different questions. Will it create many long-term jobs? Will it use too much water? Will it raise electricity costs? Will it change the landscape? Will the benefits stay local or flow back to distant technology companies? The water question is especially sensitive. Servers produce heat. Too much heat can damage equipment or reduce performance, so data centers need cooling. Some cooling methods use water, some use air, some use a mix of both. The exact impact depends on the location, the climate, the design, and the energy source. A data center in a cool region may face different challenges from one built in a hot, dry area. This is why the same technology can create very different local debates. In one place, the main issue may be electricity. In another, it may be water. In another, it may be land use or noise. Large technology companies say they are working to reduce the environmental impact. Google, for example, reported that in 2024, it reduced data center energy emissions by 12%. It also reported replenishing 4.5 billion gallons of water. And it said it procured more than 8 gigawatts of clean energy. These efforts are real, but so is the growth in demand. Google's 2025 environmental report also says its total data center electricity consumption grew by 27% in 2024. That is the central tension of the AI era. The systems may become cleaner. The chips may become more efficient. The energy may become greener, but the total scale may still keep rising. When something becomes cheaper and more efficient, people often use more of it. Cars became more efficient, but the world built more roads. LED lights use less electricity, but lighting expanded. Cloud computing became efficient, but digital services multiplied. AI may follow the same path. Better models could reduce the energy used for one task. But if AI becomes part of every search, every office tool, every phone, every video platform, every factory, and every school, total demand can still grow. This does not mean AI is bad. AI can help design better materials. It can improve medical research. It can help forecast weather. It can optimize power grids. It can make some work faster and more accessible. The story is not simple. AI may help solve problems, but it also creates new ones. The biggest mistake would be to treat AI as if it exists outside the physical world. It does not. It sits inside buildings. It runs on chips. It needs electricity. It produces heat. It depends on water, land, metals, cables, and people. The future of AI may not be decided only by algorithms. It may also be decided by power lines, by permits, by cooling systems, by local opposition, by energy prices, by whether grids can expand fast enough. The next phase of the AI race may not only be about who has the smartest model. It may be about who can build the most reliable infrastructure, who can secure enough clean electricity, who can cool the machines, who can afford the land, who can keep communities on their side. In the 20th century, oil shaped geopolitics. In the 21st century, computation may shape it too. And ordinary people may begin to realize that every digital miracle has a physical footprint. So the next time an AI answers in seconds, remember what you are not seeing. The server room, the power plant, the cooling system, the cables under the ground, the workers maintaining the machines, the community living nearby. AI may feel like magic, but it is not magic. It is infrastructure. And the question is no longer whether artificial intelligence will change the world. It already is. The real question is whether we can build that world responsibly.